Okay. Is the screen shared or not? The screen is shared or not?
Yes.
Okay. Uh, so as I said, continuous floor or called continuous beam, a new system. It's not a new system, it's an indeterminate system. So we just need to learn how we can calculate the moment and the shear force for a system that is indeterminate. So we used to, up to now, we used to analyze determinate structures. And most likely is either a simply supported beam or a cantilever beam or an overhanging beam. Okay, these are the systems that we use to analyze and design and determine the moment at the critical sections and the shear force at the critical sections as well. Okay, so let me draw a continuous beam. A continuous beam is made up of two spans minimally. A continuous beam, if I draw it this way, okay, a continuous beam is at least is supported by three supports. Okay, this would be a continuous beam. Okay, three supports and two spans. So minimally two spans and three supports. Okay, this would be a continuous beam. Or we could have a beam that is made up of more than two spans, which means three, four, and above. Three or four and above. So if I draw such a system, it would be, for example, make it three or four, four. So supported by one, two, three. So now we have two spans. Four. How many spans? One, two, three spans. And then uh, over here. Okay. So these are how many spans? One, two, three, four spans. So we need to redraw it because we have an extension. We could say that we have only four spans. Okay. So minimally two spans and as many spans as possible. You could have in case if it exceeded two spans. Could be two, it could be three, could be four, it could be five, and so on. Okay, so this kind of system is called a continuous floor system or a continuous beam system. As I said, the difference between the systems that we've been analyzing and designing is the system is indeterminate. That means we cannot determine the shear force or the bending moment using uh, equilibrium equations. Equilibrium equations uh, are not capable of determining the shear force and bending moment because they are indeterminate. They are indeterminate. And the simplest way that ACI code allows us to analyze and design this kind of floor system is by having their coefficients. We can have their coefficients. Through their coefficients, we can we can determine the uh, the shear force and bending moment. But there are conditions. One of the condition is that the span we have to have at least two spans, as I said, and the span if we have this span is like L1 and this span is L2. Okay, if I label this span as L1, this span as, let me check, this span is L1, and this span is L2. So the difference between these two spans should not exceed the difference, or you could say L1 should not be more than L2 by, or L2 should not be more than L1 by 20%. 20%, okay? That is one of the conditions that should be satisfied, okay? The other condition, loading should be a uniformly distributed load. So we should have a uniformly distributed load on the system, okay, be it live load or dead load. So we cannot analyze the system if we have a point load using coefficient method. There are some other methods like moment distribution method, other methods for indeterminate, for analyzing an indeterminate structure. So we could use those methods, but ACI code doesn't allow us to use the coefficient method if the load is not a uniformly distributed load. The other condition, live load should not exceed dead load. N-factor load of the live load should not exceed the dead load by 3 times. The N-factor live load should not exceed, so the second condition. Second, the loading is uniform, okay? Uniformly distributed load, uniformly distributed load, okay? And the third condition, live load shouldn't exceed N-factored live load, N-factored live load, okay, should not exceed 3 times dead load, N-factored dead load. Okay, this is live load, shouldn't exceed 3 times the dead load, and they are N-factor, when they are N-factor. And the span difference, and what else? The section should be prismatic. The beam should be prismatic. What prismatic is meant by when they claim that the section should be prismatic? Anyone knows what prismatic is? Hmm? Anyone knows what prismatic is? This is any prismatic chair. Nobody knows? Okay. Prismatic means that the section is of the same cross section all the way to the end. So if you have like a rectangular section or a square section, okay, so it's not like the cross section is changed. It changes from one length into another length. That is not allowed. So it should be prismatic, which means that the cross section, if it is square, then it has to be square all the way up to the end, all the way from the first span up to the end. They should be of the same cross section. That is prismatic, okay? That would make the floor system or the beam to be prismatic. Okay, when we face such a system, in reality, anybody? Okay, let me see if this two span. If we look at the plan view of a building, we have a plan view of a building. Okay, this would be the plan view. Okay, and okay, so this is the plan view for this. Assume that this is a floor system that we have. We have a slab, and the slab is supported by columns. The slab is supported by columns over here and a column over here and a column over here. And a column over here. Okay. So if this is the top view, and then we could have this hidden B underneath the slab. From the top, it look we draw it as a dashed line because the beam is hidden underneath the slab, so we cannot see it. So with a dashed line, we could draw the beam that is supporting the slab. Okay. So okay, usually is less than the column's thickness. Mistakenly has gone beyond the column. Usually should be this way. Okay. Anyway. So if you have a whole column is like this, I magnify it. Okay. So I magnify the column. So this is how it looks like. Okay. Okay. So when we design, so if I assume that my system is this one, okay, so how could I design this beam? This beam would be a continuous beam. And what kind of cross section do you think that this beam would have? If you have a slab and the slab is monolithically cast as a single unit with the beam, with the beam, with the beam. Okay, if the slab is monolithically cast and is acting as a single unit with the beam. So what kind, if I get a cross section, if I get a cross section, if I get a cross section here or here, so what kind of cross section, what kind of cross sectional shape you,
أستاذ
Bale?
بشوي L shape ده يعني.
Yeah, exactly. It would be an L shape. How about the other side? The other side?
أستاذ أنا أدري أشهر بقى L shape.
Exactly. So if we want to have like a T shape, then we have to have another span, like a T shape man a bit. We have to have another span, okay? So at that point, if I also draw columns over here, column, okay, and a column, and we have a beam, dashed line, okay. Okay, this is a beam. This would be an L shape. This beam would be of an L shape beam. And this would be, of course, we will not have this dash line anymore. This wouldn't be a dash line. It would, sorry, it wouldn't be a continuous line. It would be a dash line at this point. Okay, our internal beam. This is the column. Okay. So in this case, the beam, so how many beams we have in this system? How many? 1, 2, 3. 2 of L shape. 1, 2. These are of L shape. If we label this 1, and this is 2. Sorry. If this is 2. Okay. If this beam is 2 and this beam is 1, then this would be 3. So only one T shape. This, if we take the cross section of this, it has a T shape. We don't know if it acts as a T section or a T or rectangular. Okay, it would have something like this shape. Okay, it would be T. Of course, it's continuous with the slab. The slab is continuous up to this end and up to this end. So we have to give it this. Okay, to show that it's continuous, and this would be a B effective. We have to calculate the B effective. Okay, for positive moment, of course, because only for positive moment the beam would be acting like or would have this kind of shape. Okay, for the positive moment only. So that is what we need to learn about today, is this kind of system, and we will get coefficient for the positive and negative moments. Okay, so this kind of beam we will deal with. Okay, so now what is left to tell you is that sometimes okay, sometimes if the ending condition, now these supports, when I when I give you these supports, when I give you like hinge hinge supports, you may not be able to know if the end of the beam at this end and this end, these two ends, whether they are restrained or unrestrained. We have if like the beam, if for this system, if you look at the beam, and I give you the actual condition, I remove these hinges, okay, these hinges, I get rid of them, and I provide you with the actual condition. If I have a column, if it is supported on columns, okay, so if I draw it nicely, I think I need to redraw it again. Just a minute. Let me. Okay, so if I want to redraw the system again, if I have this, how to say this? This is our beam, and we have columns over here. Column over here, and a column over here. So for this kind of, so this is our system would be supported on 3 columns. So the beam is continuous for 2 spans and supported on 2, sorry, on 3 columns. So this, I need to admit a student. Okay, so this system is continuous and having 2 spans supported by 3 columns. This end and this end, they are restrained against rotation. That means the beam is not allowed to rotate at this end or this end. Okay, is not allowed to rotate if the beam is monolithically cast on the column. In that case, then the beam is not allowed to rotate. So this kind of end condition is called restrained condition. Restrained, that means the end is not rotating. Okay, the end is not rotating. How about if I have like the same floor system, but the ends are the same, okay, and then I have like a spandrel beam at this end, okay, not a column, a spandrel beam or a girder, and at mid, I have a column. It's supported by a column. And the other end is supported by, again, a spandrel beam or a girder, or even if there is no beam, it's possible. This is just let me, sorry, this need to be, okay, if I make it nicer, this is, sorry. Okay, so now this is the beam up to here, spandrel beam. Okay, then upward, then this way. So if you have it this way, so you will, and of course is supported by a wall. Okay, if we have a wall here, a wall, okay, a wall, and the wall, you could see is made of blocks or bricks or anything else, stones. We have a wall, okay. So this is a wall, okay. So it's resting on a wall. This spandrel beam is resting on a wall, and consider this also resting on a wall, okay. And they could be, even the wall could be of the same thickness of the beam, we have no problem, but I just want to differentiate the thickness so that you could feel that this support is not a column. Okay, that's the only reason that I'm not giving the same thickness to the spandrel beam. I mean, the thickness of the wall is not equal to the thickness of the spandrel beam, just to let you know that this is a wall, okay? This is a wall. So if even if we don't have a spandrel beam, even if this doesn't exist, it's just a slab, I mean, the beam continues up to the end and is supported by a wall, we consider that this end and this end are unrestrained. So that means is not fixed. Restrained, it means is like fixed against rotational deformation. So like, for example, when you have a cantilever, okay, I could tell you that if you have a cantilever, and of course, any cantilever is fixed at its end, right? So any cantilever is fixed. So the cantilever, is it restrained at its end, at this end? Is it restrained? When the cantilever deform, it deformed this way, right? Sorry, this way. Okay. No. Don't have enough space to show it to you, and this is annoying. Okay, if I have a cantilever, let me remove one of these so that I have enough space. If I have a cantilever, and the cantilever is fixed at one of its end, which is all the time the same thing. This is fixed. Okay, when fixed, that means you have a moment. Okay, that means you have a moment. Restrained it means that you have a moment at the end. That's why you have a moment, because it's restrained. So when it deforms this way. Okay, right? So the angle of rotation would be equal to, the angle of rotation, if we label it as theta, would be equal to 0. Okay, but for a simply supported beam, okay, if you have a simply supported beam, if you have, this is a simply supported beam, okay, with the ends, if this is the end, the other side, and this is a hinge, okay. So do we have any restraint at the ends? You see, it deforms this way. Do we have moment at the end? Do we have moment? for the cam. Yeah, Razwan.
مثل أستاذ مومنت صفر للسبورت كان.
Yeah, when the moment is equal to 0, that means you have rotational deformation. So that means theta will not be equal to 0. Theta is not equal to 0, right? Here, because we have moment, theta means the angle of deformation. Theta is the angle of deformation. Because the angle of deformation, because of the moment, the theta is equal to 0, because we have a moment that prevents this end to have an angle, to have a rotational, we call it a rotational deformation. The moment prevent this end to have this rotation. But over here, there is no moment when you have a cantilever, a simply supported beam. The moment is equal to 0 at these ends, because it's not fixed, so we have a rotational deformation. So in fact, when we model a system, a floor system that is continuous, if the end is supported by a continuous column, that means the column is built monolithically with the beam, that they act as a single unit. So we consider we have moment. We have moment at these ends. That's why we consider them to be restrained. So there will be no theta. Theta would be equal to 0. But if you have a wall, we model it as a hinge. If we have a wall, that means the end of the beam is supported by a wall. Okay, even though you have a spandrel beam, this is a spandrel beam or a primary or a girder, you could label it. Okay, then, and is supported on a wall, then we consider that this wall is like a hinge. Okay, so you will have, you won't have moment at this end. Moment would be equal to 0. So if moment is equal to 0, that means what? That means the end is not restrained, so you will have rotational deformation. Okay, so we know the difference now between the end that is restrained and the end that is not restrained. Restrained against what? Restrained against rotational deformation. How it is restrained? Is restrained by having a moment. So in such a system, do we have a moment? Yes, we do have a moment. Okay, in such a system where the end is supported by a wall, do we have a moment? No, there would be no moment at the end. There would be no moments at the end. So it's end restraint. Okay, so now we go into the coefficient, how we can I think what is left is only 3 minutes, so we log in again after 3 minutes. So this is the floor system in 3D. Any graph to show you? This is a floor system. Okay, so you see the beam is supported by columns. Okay, so it's not the complete span is not given, so we don't know how many spans we have. Okay, this is a slab supported. How many spans we have along this side and this side, it's not shown because it's just taking a cross section of both sides, so we don't know how many spans we have, how many spans over there, and how many spans along the x-axis and how many spans along the y-axis. But we could know that the beam is supporting a one-way slab. The slab is giving its loads to this side and this side. The slab is giving its weight to this side. So the shortest side would take the load of the shortest side, would transfer the load of the slab to the beams. Okay, because this side is the long side, even if it is supported at this end with columns, you see. Okay, though we don't have a beam. We don't have a beam over here. It's not shown. No, there is no beam. So the beam is continuous in only one side, in one direction. Okay. So now we go to the coefficient, how we can calculate the coefficient for moment and bending, for moment and shear force. So this is the table that is usually given to you. Okay, ACI code provide this table to us to determine the value of the coefficients. So these are the coefficients: 1/14, 1/11, 1/16. Okay. What is W over Ln, W times Ln squared? W is the ultimate load W is the ultimate load, which means W is equal to the factor dead load, which is 1.2 times dead load, okay, added to 1.6 the live load. 1.6 times the live load. Okay, this is W. What is Ln? The net span between the columns. So that means it's not center to center, it's from the face of the column to the other face of the column. Okay, face to face. Okay, if you have like this is your column, okay, and this is your other column. Okay, so this is the distance. Okay, and this is the beam, continuous. Okay,